Hello again. We're having another lesson, another class on physical chemistry, to be more specific on chemical kinetics, and we're making our next step towards a deep understanding how it works. And I have prepared some assignments for you, some questions, theoretical, both theoretical and practical, so that you practice your knowledge in order to be sure that you are quite good at chemical kinetics. Before we get down to the core of today's class, I just want to say a couple of words which you should always bear in mind. The thing is that you may belong to different cultures, different teaching schools, different universities located in different parts of the world, and your teachers, your mm, okay, instructors may keep to different notations. I mean to say that so that you've got a picture, I'd like to bring in a relevant example. Um, okay, that'd be like this. Uh, you would talk about a thermodynamic system, a gaseous one. So we can talk about the partial pressure of a particular component of the gaseous mixture, right? Uh, and we also can and should talk about the total pressure of the whole system, and we can denote it as P, uh, and as the sub-index, we can write total sub-index, right? Or in some schools, particularly in Russia, in the Soviet Union schools, in Germany, um, the scientists prefer to use so-called Greek alphabet notation. Is used a lot. And for example, instead of writing P total, they write sigma P, capital sigma P, where sigma means overall or net. I know that in India, for example, Indian professors prefer to write P net. It's also okay. What I mean to say is that it doesn't matter what symbols are used for notations of this or that particular phenomenon, but you should always be able to understand what is meant. Okay. Now let's proceed to the first question. It's not very difficult to deal with. It's going to appear on the screen of your computers in a few moments. Here it is. So the question is, how do the rate of the forward and the rate of the reverse reactions change when the total pressure in the gaseous system, and the system describes the transformation of 1 mole of A into 2 moles of B, vice versa, increases 3 times? Of course, by saying vice versa, I mean the dynamic equilibrium between 1 mole of A and 2 moles of B. Okay, so we have a system, okay, where this chemical transformation, this chemical reaction occurs. And it changes because the total pressure of the system goes up 3 times. And the question is how the um, rates change. Okay, let's do that. First of all, let me rewrite the scheme of this reaction. So 1 mole of A dynamic equilibrium transforms into 2 moles of B, right? Okay. The kinetical equation of the fourth reaction, A turns into 2B, is this one. It's rate constant K times the partial pressure of A, P of A. Okay. So it means that in the beginning, we've got this initial reaction, initial rate of the reaction, but when the pressure goes up 3 times, that means that finally the pressure increases 3 times as well. For that reason, we can clearly see that W over W sub 0 is equal 3, to 3. And we can say that in this case, the rate of the reaction, and we're talking about forward reaction increased 3 times as well. Well, physically, I always say that a good chemist, should be able to just to explain another chemical phenomenon with the help of physics. We can explain this by saying that pressure yes is proportional to concentration, the concentration of the substance. Why? Why am I saying that? Because from the equation of Mendeleev Clapeyron, we can write this, right? If we divide the both parts of this equation by v, we will get P uh, uh, is equal to nu over v times R times T. And this is equal to concentration C. For that reason, we can write that P is equal to C times R times C. That's it. For that reason, I can see that P is proportional to C. For that reason, the number of times P increases, the same number of times C increases. And if C increases, so we can say that the velocity, the rate of reaction increases as well. Now, let's consider the reverse reaction. So the kinetic equation for the reverse reaction is uh, K sub -1. -1 means that we're talking about a reverse reaction times P of B squared, right? Yeah. And this is the equation which is applicable before the pressure increases 3 times. Now, we can write the same for the same reverse reaction, but after the pressure increases. The rate constant doesn't change, it remains the same, but now the pressure, the partial pressure of B increases 3 times, and all these squared, and we got 9 times K sub -1 times P of B. And if we divide this by this will cancel each other, right? I'm sorry, squared, of course, cancel each other, and we will get 9. And we can write that the reverse reaction rate will increase 9 times. You see, the forward reaction rate increases 3 times, but the reverse reaction rate will increase 9 times. That's it. Thank you. And now we're proceeding to the next question. It's more theoretical than practical. However, finally, we will have to give a numerical result. Here it is. So, at some point in time, cyclohexane combustion rate at oxygen excess equals 0.350 moles per liter per second. Calculate carbon dioxide formation rate and oxygen consumption rate at the moment. So we got the magnitude, a magnitude of the rate with respect to cyclohexane, right? And now they want us to calculate to compute the rate of dioxide formation. Okay, let's do that. First of all, we need to write the equation of this chemical reaction. So cyclohexane formula is this one, okay, and it's burned. So we should write the formula of molecular oxygen. So it is combustion for that reason. So carbon dioxide and water vapors are formed, right? So six, 12, and 9. Yeah, let me check it again. So 6C, 12H, 18O. Yeah, okay. Now we've got the chemical reaction, and we can write that D of the concentration, the cyclohexane concentration, C 6H12 over the T is 1 out of 6 D CO2 over the T, and 1 out of 6 D H2O over the T. So where did I get these coefficients from? From the coefficients taken from the reaction. They go to the denominator always. Okay? Minus, I have put down the minus because this substance is a reagent. And here we've got positive signs because these two are the products of the reaction. Okay, now we can write that this is the rate of the reaction with respect to CH12, right? While this one is the velocity of, I'm sorry, it's from physics. The rate of reaction with respect to CO2, carbon dioxide, and this one is what? The rate of reaction with respect to the formation of water vapors. Okay, okay. Now we can write that 0.350 moles per liter per second is equal to 1 out of 6. The rate of CO2 formation. For that reason, we can write the W of CO2 is equal to 6 times 0.350. That will get a calculator to get the right answer. So 6 is multiplied by 0.35, and we'll get 2.100 moles per second. Okay, and as we see, the same, absolutely the same number will be for water vapor formation. I'm sorry, they ask us to determine the magnitude of the oxygen consumption. I'm sorry. It's not a problem at all. We can write that we should also take into consideration that in the formula, in the equation, we got the coefficient 9, which stands before O2. For that reason, we got the fraction 1 out of 9 before this relation, and always the minus sign because oxygen is another reagent in this reaction. In other words, we can write that um, yeah, okay. In in this case, we can write that the oxygen consumption rate is equal to 9 times the rate of CH12 Let me get a calculator to the calculation. So 9 times 4.35, so 3.150 moles per minute per second. So these are the answers. That's it. Thank you. Okay, let's proceed to the next problem. Not exactly a problem, maybe a theoretical question. Um, Determine the rate of a complex reaction if the rate constant measurement unit is liter raised to a half times mole raised to minus a half times a second raised to minus 1. In other words, we can write that the dimension of the rate constant is 1 mole raised to a half. Oh, I'm sorry. That's my fault. Liter raised to a half divided by moles raised to a half times a second. I'll just second. Okay. This is the measurement unit of the constant. And they want us to estimate the rate of this complex reaction. If it is a complex reaction, so it's very likely that the magnitude of n isn't going to be integer such as 1, 2, 3, or 0. It's very unlikely. It's very likely to be like a fraction, a half, a third, you name it. Okay, let's see that. Now, how can we solve this problem? We should remember that the rate of reaction is equal to K, which is the rate constant times the concentration of the reagent raised to N, right? And now we're not going to work with this equation itself, but with the measurement units of the elements which make up this equation. For example, we know that the dimension of the rate of reaction is mole per liter per second, right? Okay. And the concentration of the measurement unit of concentration is liter per mole, right? Okay. Now let's plug these measurement units into the correspondent elements or terms of this reaction. So it means that instead of W, I write 1 mole over L over S. Instead of K, I'm writing 1 L raised to a half over mole raised to a half and second, right? Times and the concentration. Instead of concentration, I'm writing a liter per mole. Liter per mole. And all this is raised to N. Okay. Now, what we do is the following. L over mole raised to N is equal to mole over S times mole raised to a half times S divided by L raised to a half. Yeah. I'm sorry. here liter, of course, mass liter per second, mass liter per second. Yeah, it means that L over moles raised to n is equal to, so mole times mole raised to a half gives us mole raised to 3 halves, or 1.5 second and second. So they both are S is in the numerator and in denominator, for that's when we cancel each other. And in the denominator, we've got L raised to 1.5. In other words, we can write that it's equal to further raised to 3 halves, right? And if we compare this expression with this one, we see that these are identical. Instead of n, so it means that n is equal to 3 halves, and this is what the rate of this complex reaction is equal to 3 halves. And now we're proceeding to the next problem. It is a bit more challenging. For that reason, you may like it even more. Here it is. So we've got an nth order gaseous reaction where n moles of A transforms into 1 mole of B, and they want us to write the kinetic equation of this reaction so that it contains the total pressure of the system. Again, in the beginning, I told you that we can stick to different notation systems. However, it doesn't, or it shouldn't stop us from understanding each other. So we can write either P total, either P net, or either sigma P, where sigma is the capital letter from the Greek alphabet. Okay, I'll prefer to write sigma P, and to which of the three you choose is entirely up to you. Okay, now let's do that. So we've got the reaction. The schema of the reaction is the following, and moles of A turns into 1 mole of B, right? Okay, in the beginning, we've got the initial pressure of the whole system, but there is no trace of the particle B in the very beginning. Now, as the transformation goes on, as the reaction goes on, the pressure of the component A drops by delta P, right? Because some moles of A is going on into auto-transformation to B, and we've got finally P sub 0 minus delta P, which is the pressure of the component A, right? And the pressure of component B is equal to delta P. So according to Dalton's law, we can write that the total pressure of the whole system is the sum of partial pressures of A and B, right? We know this from physics, and we often use it in chemistry and all the calculations related to gaseous systems. PA is equal to P sub 0 minus delta P, while the partial pressure of B is equal to delta P. Oh, I'm sorry. Delta P over N, of course, because of this coefficient. Delta P over N, right? Now, I can put these two terms together in the brackets. So I'm going to write it very in detail, okay? Plus delta P over N minus delta P, right? And we see that with two terms contain one common element, which is delta P. And for that reason, I can put it out of the round brackets. Yes, and we got 1 divided by n minus 1. And write about it is equal to 1 minus n over n, right? Okay, but I need delta p. So let me rewrite this equation. So sigma p is equal to p sub 0 plus delta p times 1 minus n over n, right? And from this equation, I can find delta p, which is equal to n over 1 minus n times sigma p minus p sub 0. Yeah. And now I can plug this into this in order to understand how PA depends on sigma P. And now, so delta P, I'm writing this expression minus N over 1 minus N times sigma P minus P0. I can see that P0 is contained in these brackets and it says here too. For that reason, I need to open the brackets to group these two elements together. So P0 minus N over 1 minus N sigma P minus, oh, plus, so minus, 2 minus give us plus N over 1 minus N P0. I see that we got P0 here and P0 here. For that reason, I put these two terms into brackets. Okay, minus n over 1 minus n times sigma p. Okay, so I put p sub 0 out of the brackets, and we got 1 plus n over 1 minus n minus n over 1 minus n times sigma p. Okay, now what I'm doing is very simple in terms of algebra. 1 minus n plus 1 over 1 minus n minus n over 1 minus n times sigma p. Yeah, I made a mistake somewhere. Hold on a sec. So delta p n over 1 minus n sigma p minus p0. Okay. PA is equal to P0 minus delta P. So delta P, I'm writing P0 minus N. Okay, okay. Now I'm opening these brackets. Minus, okay, plus N, okay, P0. So P0, I group this into one brackets plus, yeah, everything's fine actually. 1 minus n. Oh, plus n, not 1. It's n here. Okay, I'm sorry. So, and minus n cancel each other. And finally, we got p0 over 1 minus n minus n times sigma p over 1 minus n. As we can see, these two fractions have got the same denominator. For that reason, we can write that it is equal to p sub 0 minus n times sigma p over 1 minus n. Yeah, okay. Now we've got the expression. Let me rewrite it. So p of a is equal to p0 sub 0 minus n times sigma p. Again, by sigma p, I mean the total pressure of the system over 1 minus n. Okay, and now I should recollect that the rate of the process is equal to K, which is the rate constant times the partial pressure of A raised to N, right? And instead of PA, I plug in this expression. It means K times P sub 0 minus N sigma P over 1 minus N raised to N. And this is the answer, because they wanted us to write the kinetic equation so that it contains the total pressure of the whole system. Here it is. That's it. Thank you. So I hope that you haven't got tired a lot and ready to participate actively in uh, developing the solution to the following problem. I wouldn't say it's a problem. It's another theoretical question, but it's very tricky. It's very tricky. So the rate constants of the forward and reverse reactions are equal to 2.2 and 3.8 liters per mole per second, respectively. Which of the mechanisms below can correctly describe the two reactions? Well, don't jump to conclusions, okay? Um, it may seem to be correct at first sight, but as the Americans say, so you should sleep on this idea in order to be sure that your um, answer is correct, especially when you deal with physical chemistry. Now, let's take a look not at the magnitudes of the two components, but at their measurement units. Let me write it. So the D of K1 is the same, identical to the D of K minus 1. Again, I want to say that sub index minus 1, it means that we are talking about reverse reaction is equal to 1 liter per mole per second, right? And because of this, we can infer that it is the second rate of the reaction. And it means that it is the second rate of reaction for both forward and reverse reactions. Not only the forward or not only reverse reaction rate. No, we are dealing with a system where we got a dynamic equilibrium. Yes, it's okay, but both forward and reverse reactions rates are 2. And for that reason, this is the key. By the way, this symbol means that's why, yes, in mathematics. This is the key to understand which one is the right answer. Let's take a look at variant option A plus B. Dynamical equilibrium and transforms into D. A plus B, we can write that for the rate of the forward reaction is K1 times A times B, right? And we can see that the rate for this reaction is 2. But let us write the kinetical equation for the reverse reaction. It's K sub minus 1 times the concentration of D, and it's raised to the first. It's raised to 1. It means that N is equal to 1, but should be 2. For that reason, A is incorrect. Let's take a look at option B. A plus B. The products are B plus D. Here, everything seems all right because the rate of the forward reaction is K1 times A times B, and it means that N is equal to 2. That's for the forward reaction, and the rate of the reverse reaction is K sub minus 1 times B. Oh, I'm sorry. I'm sorry. That's double T, yeah? No, double T. It's 2D. For that reason, K sub minus 1 times the concentration of D squared, yeah, because of this coefficient 2, and that means that N uh, sub minus 1 is equal to 2, and it's okay. It's okay. It means that this scheme, A plus B turned to 2D, is okay. It corresponds to the dimensions of K1 and K sub minus 1. Let's take a look at C. Reaction C, A, B plus D. It's clear that N of the forward reaction is equal to 1, and only the rate of the um, uh, reverse reaction is equal to 2. But we need both of them to be equal to 2. For that reason, it's not okay. Now let's take a look at the last one, D. 2A and just B. Okay, I guess that you've got the picture. And the rate of the forward reaction is equal to 2 because of this coefficient. But the rate of the reverse reaction is equal to 1 because the coefficient before B is equal to 1. For that reason, it's not okay. In other words, the only correct answer is option B. Again, let me rewrite it. So A plus B 2D. A and B both have either of the two have a rate of 1, yeah. So the rate of the forward reaction with respect to A is equal to 1, and the rate of the forward reaction with respect to B is equal to 1, which means that the total rate of the forward reaction is equal to the sum of the two of the two rates. I'm sorry, not rates. Oh, my head isn't working. Okay, 1 plus 1 gives us 2, right? And here we've got 2 before D, which means that we should raise the concentration of D to the second degree or squared, and that means that that is also equal to 2. Yeah. So it means that only B is consistent with the measurement units of the two constants. Thank you. Okay, now I hope that all of you are ready to proceed to the next problem. It is a problem which needs to be solved. Hydrogen iodide decomposition is a second order reaction with a rate constant K equal to 5.95 times 10 raised to minus 6 liter per mole per second. Compute the rate of the reaction at 1 bar and 600 Kelvin. You may be surprised to see the word bar. Bar is another, I mean to say that it's one of possible measurement units of pressure. So you may get accustomed to dealing with pascals, right, or atmospheres if you're engineers. Atmospheres, most chemists and physicists deal with pressure taken in pascals, but these days modern physicists and chemists prefer to use bars as the main measurement units for pressure. And in order to be able to operate it correctly, you need to understand that 1 bar is equal to 1 times 10 raised to minus 5 pascals. Okay. Okay. Now, in order to compute the magnitude of the rate of the reaction, first of all, let's write down the kinetic equation. It's K, which is the rate constant times the concentration. Okay, let's write it, this one. The concentration C of this reagent, yeah, hydrogen iodide. And it is the reaction of second order, for that reason we should square it. Now, I hope that now you can see that in order to do these calculations, we need to know the magnitude of the concentration of HY. How can we do that? So, we are dealing with a typical gaseous system. For that reason, we can apply the Mendeleev-Clapeyron equation, which is P times V is equal to nu, which is the number of moles of this component times R, gas constant times T, right? Okay, let's divide these two into V, and we will get P times nu over V times RT. But this term is equal to concentration C, moles per cubic meter, a cubic meter, yeah? CRT. Okay. Now, we must be very careful with the measurement units because as chemists, we are used to dealing with little per moles. We would talk about concentrations, but physicists keep to C system, which means that instead of liter, they use cubic meters. Okay, it's not a great problem, absolutely, because we can substitute 1 cubic meter into liters, knowing that 1 cubic meter contains 1,000 of liters. Now, let's proceed to the calculations themselves. We can write from this equation that the concentration of hydrogen iodide is equal to the pressure divided by the gas constant R and the temperature. Yeah. Okay, we've got the temperature. We know how much R is, and we've got the pressure. It is 1 bar, but let's substitute 1 bar with the pascals. It's more convenient for me personally. Okay, and R is equal 8.314 joules per mole per Kelvin, and the temperature is equal to 600 Kelvin, right? It's very good. And now we can write that it's equal to, let me calculate, 1 second, please. I want to just write that 1 bar is equal to 10 raised to minus 5 to plus 5, of course. Oh, it's my stupidity, I'm sorry. Okay, in this case, we got 5 divided by 8.14 and divided by 600. Yeah, it's 20.047 moles per cubic meter. Okay, meter cubed. Yeah, but we should prove it. So the dm of the concentration is equal to, so Pascal joule per mole per Kelvin and times Kelvin cancellation. So Pascal is equal to Newton over a square meter, right? While if we divide Pascal to this fraction, so we got finally mole per joule, right? So Newton over square meter mole, and instead of joule, we write Newton times meter cancel. So we got 1 mole over cubic meter. Yeah, we proved. Okay, so we got 20.047 moles for a cubic meter. Uh-huh. This is the concentration, but again, we are accustomed to dealing with moles per liter. For that reason, we divide this by 1,000 because we remember that 1 cubic meter contains 1,000 of liters. And finally, we can write that the concentration of HY is equal to okay, roughly roughly 0.02 moles per liter. Okay, and now we can substitute this into this formula. So the rate of this process is equal to it's okay, right? It's magnitude 5.95 times 10 raised to minus 6 liter per mole per second times 0.02 squared moles per liter, but a squared too, but that's when we write mole squared, liter squared, right? Cancel, cancel, and finally we got, looking to calculator, okay. So it's equal to 2.39 times 10 raised to minus 9 minus mole per liter per second. Yeah, this is the answer. And again, we have proved the correctness of our calculations by seeing that the measurement of the rate is 1 mole per liter per second. That's it. And whenever we're making, I'm sorry, whenever we're doing such physical calculations, we should somewhere parallelly write these dimension calculations as well to prove that we are standing on the right track, as I have just shown you with the rate of reaction. But finally, we've got moles per liter per second. Thank you. Okay, now we are proceeding to the next problem. Here it is. When the Saccharose inversion kinetics was explored, the following findings put into the chart were obtained. The chart contains two lines, the time line and the concentration of saccharose line. Calculate the initial rate of the reaction is assignment A. And question B, they ask us to compute the average rate within the first 90 minutes. Okay, let's do that. So A. In order to be able to calculate the initial rate of the reaction, we should remember that W sub 0, which denotes the initial rate of this reaction, is equal to K times the concentration of this substance. Let's designate it as A, okay? Because it's so long to write it down, I need to minimize the space of the computer screen, because it's going to be a lot to be written on it. Okay, and I also can assume, again, it's my assumption that the inversion is a first order reaction. Okay, it's only my assumption, and I need to prove it by calculating K, first of all. Again, you see that in order to compute W sub 0, I need to know the magnitude of K. To do that, I assume that n is equal to 1. For that reason, I can use this formula. K is equal to 1 over t times natural logarithm and logarithm from the fraction. The denominator of the fraction contains the initial concentration of this substance, and the denominator is current concentration at time t. Okay, let's do that. So we can write that K1 is equal to the first time is 30 minutes, right? Natural logarithm, the initial concentration is 0.5, and at 30 minutes, the concentration is 0.451. Okay, let me take a calculator in order to get the answer. Okay. Logarithm now we divide by 30, and we got 3.44 times 10 raised to minus 3 minus raised to minus 1. Okay, that's K1. Now, likewise, we calculate K2, its magnitude. This time is 1 out of 90 times the natural logarithm of 0.500 over 0.363. Let me have a look. What my calculator will tell me how much it is. Okay, now we divide by 90. Yeah, it's very close. It's 3.56 times 10 raised to minus 3 minutes raised to minus 1. Okay. Now K3 is 1 out of 130 natural times natural logarithm of 0.500 over 0.315. We got 355. 355 times 10 raised to minus 3. Okay, and the last one, K sub 4. Okay. Yeah, very close. It's 3.49 times 10 raised to minus 3 minus raised to minus 1. As you see, the magnitudes of the found K's are very close to each other. So that's what we can confirm that the assumption that the rate is that n is equal to 1 is not groundless. Yeah. And now for further calculations, we need to get the average magnitude of K. We can do it by summing all found K's and divide the sum by 4. 1, 2, 3, 4, yeah, by 4. The mathematical symbol of sum is a sigma. Again, it's coming back to what I said in the beginning. K sub I. Okay, and let me do a calculation. So it's 3.44 plus 3.56 plus 3.55 plus 3.49 times 10 raised to minus 3 and 1 out of 4. Also completes. So 3.44 plus 3.56 plus 3.49 55 plus 3.49 and we've got 3.51. This is the average value of K3, the average 3.51 times 10 raised to minus 3 minute raised to minus 5. Okay, and now we can calculate the initial rate of this reaction is 3.51 times 10 raised to minus 3 minute raised to minus 1 times the initial concentration of saccharose. It's 0.5 mole per liter. And let me take a look at this. 1.755 times 10 raised to minus 3 moles per liter per minute, because minute is raised to minus 1, which means it should be in the denominator. Yeah, and we've got the correct measurement unit for the rate of this process, and here is its initial value. But this is the answer for A. Now we are proceeding to B, part B. In part B, they ask us to calculate the average rate within the first 90 minutes. It's a very simple arithmetic operation. So the mean value of W from 0 to 90 minutes is equal to the initial concentration of saccharose minus the concentration of A at a time 90 minutes, right? And we divide it by delta T, which is equal to 90 minutes. 90 minus 0. At 90, it is 0.3. I'm sorry. In the beginning, the concentration is 0.500 minus 0.363 at time 90 minutes, and we divide by 90. Let me have a look. So it's equal to 1.52 times 10 raised to 2 minus 3 moles per liter per second. This is the answer for question B. But it's relatively easy in terms of calculation, but you may be asked to determine the instant reaction rate at the time which isn't included into the chart. For example, it might be like this. It's a very provocative and very difficult question to deal with. For example, like this. Determine the instant rate of the reaction at time of that'll be 40 minutes. But 40 minutes information isn't included into the table. In this case, what should we do? I hope that this is clear as day for you that in this case we can talk about only approximate values, and we can do it by drawing the curve, the counter curve for the saccharose concentration dependence on time. And then graphically, we can get the approximate value of this concentration at time t 40 minutes. But that will not give us the answer to the rate. In order to get the rate, we can, for example, find from the graph, we can find the concentration of, the concentration of A at time, that'll be for 35 minutes, right? And to get from the graph the concentration of sucralose at time it's time 35, and the concentration of sucralose at time, let me 45 minutes, yeah, very close to each other. These two time points are close to each other, and that narrows down our calculations, and automatically it makes the average W calculations close to the instantaneous rate of calculations, right? Because we remember that the more narrow the time distance between two time points, the more accurate our calculations are, because in this case, the average rate comes closer to the real or instantaneous rate. Again, the answer is that we can do it from plotting the graph of the curve. One of the uh, possible solutions. Another possible solution is that with the help of computer program, for example, Excel, we can plot this data, right? Then it will give us the line of approximation. In other words, that will give us the equation how W depends of T. We will get some function, and we can then get the derivative. Yeah, derivative if needed. No, actually not in this case. So we will get the function f of t, right? And then we substitute 40 in this formula, and we will get the value of W. It's another possible way with use of computer. Okay, thank you. Now, let's proceed to the next theoretical question. We got forced information kinetics, which is described by the equation, which is given. It's not that easy, by the way. And they ask us to estimate the net or total rate of direction when the concentrations of chlorine are high, and in the another extreme when these concentrations are low. Well, let's write it down. So situation A, high concentrations, high chlorine concentrations. When the chlorine concentrations are high, that means that K prime times chlorine concentration is much, K double prime is much bigger than K prime. For that reason, we can neglect K double prime, and the whole kinetic equation can be rewritten this way. K times CO concentration times chlorine concentration raised to 3/2 over K double prime concentration of chlorine. And in this case, after very simple arithmetical, we can say operations, we got K over K double prime times concentration CO times chlorine concentration raised to half. And for that reason, the I'm sorry, not the rate. Yes, the total order of this reaction is equal to 1 with respect to CO plus a half with respect to chlorine. In other words, it's 3 halves. It's at high chlorine concentrations. Now, in B, at low chlorine concentrations, we can neglect this time. We can neglect K double prime times chlorine concentration, and for that reason, this kinetical equation can be written this way. The denominator is the same. It's K times CO times chlorine raised to 3 halves over K prime. Yeah. And it means that N in this case is the sum of 1 with respect to CO plus 3 halves with respect to chlorine. In other words, it's 5 out of 2. That's it. Again, let's summarize this. At high pressures of chlorine, or which automatically means at high concentrations of chlorine, the total order. I'm sorry, it's not rate, of course, order. The total order is equal to 3 halves, and for when the concentrations of chlorine are low, the total net of the reaction is equal to 2.5. And now we're proceeding to the next question. A methane bromide decomposition is described by the following kinetic equation. You can see it over here. As you see, we have no fraction. We've got two terms summed to each other, and they ask us to determine the rate. Again, the rate, of course, not rate, not the rate, not the rate, but the total order. Let me write here, order, the total order of the reaction at high and low concentrations of methane bromide. Let's do that. Let's do that. Let me rewrite it. So d of CH3 Br over dt is equal to K times the concentration of the substance plus K prime times the concentration of the same substance, but raised to 3 halves. Now, in this case, we have no fractions, no numerator, no denominator is seen in this equation. For that reason, the simplifications which we could do in the previous questions are not applicable in this one. So what can we do in this case? First of all, I just want you to understand that whenever we don't have a clear way in mathematical terms, we can turn to arithmetics. Absolutely. Let's imagine that the concentration of CH3 bromide is equal to, and let's take a very, very low concentration, but specific one, let it be 0.0001, okay, moles per liter. As you can see, it is a very, very low magnitude of the concentration. Well, and if we plug this magnitude into this equation, what we will get? We will get that W or omega, it's another Greek letter, omega is equal to K times 10 raised to minus 4, yes, plus k prime times 10 raised to minus 4, and all this raised to 3 halves. So it means that is equal to k times 10 raised to minus 4 plus k prime raised to, times 10 raised to minus 6. Minus 6. As you can see, in this case, k times 10 raised to minus 4 is much more than k times k prime times 10 raised to minus 6. What conclusion can we make? Whenever the concentration of this reagent is pretty low, we can neglect the second term. We can neglect. And in this case, the rate, oh my gosh, again. And in this case, the rate of this reaction can be written like K times the concentration of CH3Br. That's all. Because the value of this term is much less than this one when the concentration of CHBr is pretty low. Now, let's take the concentration of this reagent as, let it be 100, okay? Let it be so. So 100, in this case, W is equal to K, okay, times 100 plus K prime times 100 raised to 3 halves. Okay. So 100 raised to 3 halves is equal to 1000. 1000. In this case, we can say that this term is much more than this one. And in this case, the more, the higher concentration we get, the more the first term is lower than this one. In other words, we can neglect the first and write that at high concentrations of this substance, the rate of this process can be written as K prime times the concentration of this substance raised to 3 halves. That's it. You see, sometimes not algebra, but arithmetics can help us. That's it. Let's proceed to the next problem. It's interesting. Thermal ozone decomposition reaction is described by the following set of kinetic equations. You can see them written. And they ask us to write a possible mechanism of this decomposition, which is which is based on these equations. So let's do that. Let's do that. It's very easy to do. Why? Because surprisingly, I need to pay more attention to sub-indexes, and they are the following: K1, K-1, and K2. It means that I've got one of the possible reactions is when we have a dynamic equilibrium and K1, K minus 1. That's going to be the first step or the first stage of this process. And the second is something like this, K2, K sub 2. Well, I guess seeing that seems it's not a big problem for us to guess a possible scheme or mechanism of ozone decomposition. The first one is an equilibrium when O3 decomposes to oxygen and oxygen atoms. A1 and Q minus 1. And then as it is an atom, for that reason, in chemical terms, it is a very, very active particle. It attacks another molecule of ozone, and it produces two molecules of oxygen. And if you write kinetical equations for these three participants, you will see absolutely these equations. Let's do that, for example, for atomic oxygen, or atomic oxygen, for example. Now we see that atomic oxygen takes a part or participates in this part stage and in this stage. But this stage is an equilibrium. For that reason, we will get two equations here and one here. Two terms from this equation and one term from this equation. So it's K1 times the concentration of ozone, because ozone decomposes and yielding O. But at the same time, atomic oxygen attacks oxygen molecule to get O3. For that reason, we got the second term of this equation, of this chemical equation. And now we pay attention to the second, where O is consumed to produce molecular oxygen. That's when it's minus K sub 2 concentration of O times the concentration of ozone O3. Now let's compare this with this one. K sub 1 times O3 concentration minus K sub minus 1 times concentration O times concentration molecular oxygen minus K sub 2 times concentration of O times the concentration of ozone O3, the same. And if you do similar things for the concentration of ozone and for the concentration of oxygen, you will get absolutely identical equations. You can do it on your own. And that means that this mechanism is correct. Now we're proceeding to the next assignment. Here it is. A kinetic curve for the intermediate x is shown in the graph, not the dependence of the rate of direction with respect to the intermediate upon time or against time. So in order to do this assignment correctly, we should recollect some important advanced mathematics rules and theorems before we continue. So we can see that this curve has a maximum, is here. This is the maximum point of the concentration, right? And let us determine the time when the concentration of the intermediate reaches the peak. So let be T sub max. Oh, it's not here. So not here, of course. Down to the time axis. Yeah, and this is the time point t sub max. Okay, okay. Now we see that from this point, from 0 to T max, the concentration of the intermediate goes up, reaching a peak, right? In mathematical terms, it means that for any point of time taken within this interval, um, the derivative of this function is positive. Now, I have said out these three words, but let's use uh, high level mathematical notation to say the same. Um, Hold on a sec, please. We can write the symbol any in mathematics is this one. For any t which belongs to the interval from 0 to t sub max, the derivative of the function x is positive. Wow. Now, from this point onwards, the concentration of x goes down, right? It falls. We can write that for any t from the interval t sub max plus infinity, the derivative dx over dt is negative, and the dx over dt at t, which is equal to t sub max, is equal to 0. On the basis of these, we can plot some scheme of the some scheme, because what is it? What does it mean? Uh, rate rate of the reaction is the change in the concentration of X with time, right? For that reason, we can mm, we can draw the following. So now this is dx over dt. Okay, and here is this time point t max. We remember that we remember that from 0 to t max, the derivative is positive. This is the initial point. Okay, it's positive, but at this point, the derivative is equal to 0, and yes, it intersects the t-axis. For that reason, it means that it's equal to 0. And from t max onwards, it's negative. It goes down. This is the approximate plot of the dependence. Thank you.